So what are the things I did? I did described AVL trees, where the constraint is that the height difference between the left and right is at most 1. We didn't really do any implementations. I just argued that the height is log n. Then we saw red-black trees. For each node has a color, red or black, and so there is a constraint of black height at every node. The number of blacks from that node to every leaf, that number is the same, and no 2 consecutive reds in a path. And here again we argued using black height that the height is log n, 2 log n at most, and we went through some insertion algorithm, a bunch of cases, and then towards the end I also mentioned about B trees, which are really used in practice in databases. So here, instead of having one node, one value at a node, you have some large number. So each node has internal node at least t children and at most 2t children. Okay, for some parameter t which is greater than or equal to 2. And I sort of hand waved to show that conceptually insertions and deletions are relatively simple. It's all the question of, so when you insert okay, so if you have t children, you also have t minus 1 values guiding you to the subtrees. Right, so you'll have like some t minus 1 values, and then each subtree will be more of the same. So at least t children, so you could have even more. And then if you have whatever k children, then you will have k minus 1 keys. So all the values here are less than or equal to this, anything here is between this, and so on. So the search is again easy. You just do a binary search here to say where to get in and keep doing it. And the height is log n to the base t. So overall it's log n to search. Now insertion, we always insert it at a leaf. So I will come to a leaf and maybe insert my new node here, as long as it's equivalently greater than or equal to t minus 1 values, and at most 2 t minus 1 values. Right. So if you have at most 2 t minus 1, even after adding this value, you are done. Otherwise, if this has become full, then you are going to split it, right? Split it as t minus 1 values in one side, t on the other, and there is an extra node which you will now insert this to your parent node and recurs upwards, because the parent may be full now and you have to do the splitting. Okay. There is also a top down version of insertion where, as you are doing binary search to figure out where to insert, if you encounter a full node, you split it then and there. Right? If you encounter a node with 2 t minus 1 values, you can just split it t minus 1, t minus 1 and give 1 to the parent. Right? So then as you go down, when at the time when I want to really insert this, and if this is full, you split it, give this to the parent, parent won't be full because you've already ensured that. So your insertion will stop there. Okay. And deletion would be somewhat symmetric. The only difference is you may not necessarily delete from a leaf, you might delete from an internal node. But again, you can, so if I want to delete something from this node, I want to delete this, then I will just see if I can get something from my sibling, right? If this has enough values, then I am going to push this up, put that guy down, so this is fine, and so one element is out here, so that particular subtree will now become a subtree here. Okay, so it's as simple as that. But you don't have enough to borrow from your sibling, then both have few values. You can merge them and pull something from here from the parent, because it's t minus 1 plus t minus 1 plus 1. These parameters are chosen in a way that you can pull this guy and have merge them, and now you need to delete from your parent and recurse upwards. Okay, so that's some sort of a quick tour of some, I didn't do any one completely, but it's useful for you to know all these data structures and, conceptually how insertions, deletions work. They can actually do a lot more. These trees, they can do split, meaning in your set, I want to give a value x and say, tell me all those which are less than x and greater than x, and telling them is easy because you can do binary search and figure them out, but you also can create two trees of the same kind of all those which are less than x, greater than x. Okay, and there is something called join. If I'm given some two trees S1, S2 and value x with the property that anything is less than S1 is less than x, anything in S2 is greater than x, you can join them. Right? I mean, you can of course put x as a root and put S1 here, S2 here, but that may not satisfy all the properties or the invariants you want here. So after doing that, you can also do all the fixing necessary to make it of the type tree you want. Okay. So today what I'm going to, so this is an, this dictionary problem or data structures to implement insert, search, delete have engaged people so much that there are some 30, 40 papers on them. Okay. So what I will do today is to again give you some guided tour of some developments in the last 25, 30 years in this. Okay. More average case data structures, amortized. So it will also be a tour, so I may not really prove anything, or maybe I will prove one thing, but the idea is to just sort of expose you to things so that you can look up and find more. Okay, so the first thing I want to talk about is what are called skip lists. This is, all this is 60s and 70s, I would say, whereas this is late 80s, early 90s, 89, 90s when this thing started. Okay, so the problem is still the same. We want to support insert, search and delete in logarithmic time. Okay. So let's start with a simple linked list. So let's say I keep a sorted linked list. Okay. So that means 7, 12, 15, 21, 25, and so on. And if anybody attending Saket's big data course, no, okay, you are. Okay. So this has the idea of this L0 sampling or geometric sampling he was talking about. So what we'll do is, so we are going to have, so the problem with linked list is that you can't do binary search easily. That's the problem, right? So I'm going to keep every other element in a second list. Okay. So and so on. And then every fourth element in the third list. So let's call this L1, L2. L3 will have every fourth element. L4 will have every eighth element. So how many lists will I have? Log n many lists, right? So the last list will have one element. And I'm drawing like this because you somehow can implement it in a way that for every element you know the next pointer in ith list, whatever list it belongs to. Okay. So how would I search for an element here now, right? So you give me, you have a query element x, I want to know whether x is in the list. We know that if I just had this alone, I wouldn't be able to do it easily. But with all this multiple lists, so what I will do, yeah, so sort of like binary search. I mean, you can't do binary search because it's a linked list. So what we'll do is we'll go to the log nth list, which will have actually the n by 2th element. And so my x, I query with that element. So that element value is there, and I figure out whether it's bigger or smaller. If it is bigger, then I go down to the next list and compare on the right. The next list element will be here, and suppose the element is even bigger than this, then I can keep going until a point I reach where it's the element I'm looking for is smaller, then I know it is here. So I'll go down. Okay, maybe I should have the previous pointer. Not necessarily. I'll go down to the next element in the previous list like this. Okay. So the search will go like this. Finally, every element is in the last list, so you can figure out, convince yourself that it's going to be log n time. Yeah, so imagine that an element, okay, so first of all,
Everyone has the elements, the other ones only have pointers to.
Yeah, so you can have implementation. So basically, an element is in Li implies it is also in Li minus 1, okay, right? So all I have is just the elements. You can think of it like this. So I have E, an element E, and next one, next two, right? So the next pointer, next element in list 1, next element in list 2, next element in list 3, and in all the lists it's part of. Okay, so it's basically this picture I have drawn. Okay, so I start with the element which is in the top list. It has an x pointer in every list it belongs to. So I compare and say, okay, oh, you are too big for me. So I come down to its next list, the previous list. I have the next pointer, compare it with that. Oh, that's small. Okay, so then I go to the next pointer of that element and so on. Okay. So it has a flavor of this doubling binary search you would have seen in your first assignment. It's a mix of both. So you can yeah, so you can convince yourself that it actually takes you log n time, order log n time to do this search. The search is fine, but how do I now insert an element, right? That's a mess. I can follow through and figure out where I should insert, but suppose you tell me that I have to insert here. Yeah, all kinds of things happens, right? Because now this element is no longer in the second list or any of these big lists it belongs to, and so this element now belongs to second list, and depending on its position from the beginning, it may be part of other things, but various other things should be deleted. It's a mess, right? So what are we going to do? When in doubt, we are going to randomize. Okay, so what does that mean? Okay, so I'll tell you how the insertion works. Okay, yeah, so search works exactly like this. So now I'm going to just step back. No, the structure is no longer like this. Okay, the structure is as follows. Every element is list 1. Then for each element, independently, I will toss a coin. If it comes head, I will add it to the next list. If it comes tail, I stop. So I keep tossing coins as long as adding it to the next list. And I do this independently for each element. Yeah, so everything. So the insertion is now very simple. The search is the same because I start from the topmost list, compare and do and figure out where I want to insert. Let's say I want to insert here. Now I toss coins to figure out where to insert, which other list to insert, and I stop where, if you get a tail. Okay. So now whatever nice properties we argued can be argued on expectation, because it's just a fair coin with probability half. I'm adding things in. So what is the expected size of L2? Half of them, because with probability half, everybody is going to come to head and then or tail, and I'm adding it. Well, expected size of this is going to be 1/8 and so on. So the expected number of lists will be log n. So the expected search time will be log n, and insertion, follow through, and then you toss. And deletion is fairly easy again. You just you don't have to. Deletion is also a mess. Is in second list, every fourth element. Then when you delete some, you need to fix various. Follow through, delete it, gone. That's it, right?
So when we insert, again we do the randomized.
Yeah. When you insert, you follow the search, and it tells me I have to insert here. And for that element, I independently toss coins, and if I get ahead, I'll. So now, yeah, as long as I get ahead, I'll keep on adding it, and I get a tail, I'll stop. Now I need to know where I should, so suppose I add it to the next list. I have to do this pointers business, right? So I need to know this element, but that is determined by my search algorithm. The search algorithm followed a path. So I remember, I came down here, here, here. I went here, came down here. So this is where I'm inserting. So I know if I remember all that, it tells me exactly where all I need to insert this element if I succeed in adding it to the next list. Okay, so end of story. Of course, you need all this expectation and tail analysis all needs to be argued carefully, but nice simple structure. Okay, so that's all in skip list. So here is another useful. Okay, so suppose elements are coming in, and let's say I'm doing insertion into my binary search tree without doing any rotation, any balancing, nothing. I just follow through the search path, insert it where it should belong to. Okay, and at the end of it, I have a binary search tree, right? So I might get 7, 12, 4, 8, 15. Let's say this is the keys that are coming in. I'll add 7 here, and then binary search tree will say 12, 4, 8, and 15. This is a search tree I'll get, right? How 8 got inserted, because I'll search for 8 here. 8 is in the right subtree, compare it with here, and 8 moves to the left subtree, I'll insert it here. Then I get this search tree, right? What would be the worst case time for building this search tree in this fashion? Okay. And in square how? Why?
First element it will take like one operation. Second might take two based on like the height. So if the height keeps on increasing concurrently.
So what would be a permutation for which it will be n square? Sorted order, either increasing order or decreasing order if you give me. Right? If I insert like this, if the elements are 1, 2, 3, 4, 5, 6, 7, 8, then what would be my search algorithm? I'll insert 1 here. Now to compare 2, I'll compare it with it, and I know it takes me to the right subtree. To insert 3, I will do my comparison, 2 comparisons. To insert 4, 1, 2, 3 comparisons, and so on. So it could be 1 plus 2 plus 3 up to n minus 1. Or if it is coming in other sorted order, it will be n square again, right? One question is, what if it is not, what if it's a random permutation? Okay. What does that mean? I'm asking. Another way to view this is, what would be the average time, right? Suppose I do this over all permutations. In this, for this permutation is n square. For a descending order permutation, it's n square. For some other permutation, it takes some other time. Okay, and you take them all and compute the average. What would be the average running time? Okay, I mean, yeah. So why? I mean, just a guess. Um,
If we can assume something for n, and then based on all the permutations, we can try to insert the n plus 1 element.
Yeah, so this I mean, it is n log n. It requires some careful calculation, but instead of doing the calculations, I will actually, what I will do is I will okay, I'll let you figure out where I'm coming from. So let's see. So I'm trying to insert some a1, a2, an, and I'm building a binary search tree on this. And a1, a2, an, let's assume is 1 to n and some permutation. Okay. How many insertions will compare with the root? Every insertion, right? So I'm going to count my comparisons in a different way. I'm trying to count the total number of comparisons, let's say, and then divide by n factorial. So every insertion will compare with a1. Okay, so a1 will go here. And maybe somewhere else some other root comes here. So how many will compare with this element? Which insertions will compare with the root of the left subtree of a1? All the elements less than a1 you will get compared with this, and all the elements greater than a1 will get compared with this, and so on and so forth. Okay, so
it's n by 2. On every n by 2 elements.
yeah, maybe, but I want you to just sort of relate to something else we have seen.
It's like a recursive automatic type. D of n is equal to
So it's yes, exactly. So I mean, in fact, the recursive, if I want to do the total number of comparisons, T of n will be something like n, because everybody will be compared with a1, plus T of I plus T of n minus I minus 1, something. If I elements fall here in my final binary search tree, or in this, if this happens to be the I plus first smallest element, if this happens to be the I plus first smallest element in the list, then exactly I elements are left of this, and they will all be compared with, I mean, whatever number of comparisons you need to insert this tree, and similarly, this will be like n minus I minus 1, but I don't know I, so there is certain probability here, and you need to, right? So what is the probability that this would be the ith or I plus first smallest element? That will be 1 over n. So, it will be 1 over n summation I. Now, if you remember, this is exactly the way we analyzed quicksort average case performance, because instead of n, it will be n minus 1, because you take a random pivot, you are comparing with everybody, that is the first step, that will take you n minus 1 comparisons. And after that, you have some I elements to the left and n minus I elements to the right, and you are recursively sorting them. What is the probability that it's I smallest, or there will be I elements to the left, it will be 1 by n, sum over all I into the averaging, and that is what it is. So, this has a very similar flavor to quicksort running time.
Then the probability that the height is
Yeah, so that's the next thing, exactly. So, so let me write the two results. Expected number of comparisons to build a binary search tree, where the expectation is over all permutations. This is order n log n, very similar to quicksort. And it turns out actually the expected height of such a BST, this is randomly built binary search tree, is also order log n. I mean, this does not immediately follow from here, but you need some tail analysis and argue something about it. Again, some useful facts, I am not going to really prove them, but at least this you can prove it. This requires a bit more work to argue, but along the same lines. Okay, so now one thing we did, so quicksort expected analysis can also be interpreted as I do a deterministic quicksort, right? I pick the first element as a pivot, partition, continue, recurse, and look at the running time and run it over all permutations and take the average, that is n log n. Okay. Yes, but there is a randomized quicksort, which is not just this first element as pivot, I pick a random element as pivot and argue. And I discussed the plus and minus of this. Do you remember what was the advantage of the randomized? Independent. It is independent of distributions, right? So, because the other one says that I run over all permutations, every permutation is equally likely, then I have this average, but it may not be true, because in practice it turns out many of the permutations are almost sorted or something, and quicksort behaves very badly, the deterministic version of quicksort. So, a randomized quicksort is fine for that, because it is the bad behavior is based on the random choices the algorithm makes, regardless of what the input is. Okay. But one way to make the permutation equally likely, can you think of a way? Right. So, let us say I want to use deterministic quicksort, okay, but I have no clue about the distribution. Choose? That is exactly what I want to avoid. I mean, that is the randomized pivot, that is the randomized quicksort, and that is good thing to do. But suppose I want to do deterministic quicksort with some pre-processing. So, what kind of pre-processing can I do? Because I do not know the distribution. I would want to do randomization, but not random pivot. So, what I can do is I can randomly permute the elements, my input, right. The moment you gave me the input, I apply some random numbers and randomly permute them. Then it is behaving like all permutations are equally likely, because the randomness is built in there, and there I can do deterministic quicksort. Okay. So, now something like that I want to do here. Elements are coming in. So, if you give me all this, then I can randomly permute them and build my binary search tree, and I can argue these nice behaviors. But the elements are coming one at a time. Okay. So, how would I have the effect of randomly permuting it when I do not have all elements in advance? Okay. So, this was a very cute solution. So, is the question clear that I just add, insert elements as they come along and build my binary search tree, and I can argue that if all permutations are equally likely, then it has this nice behavior. One way to achieve it is just randomly permute them and then build this binary search tree, but maybe not all elements are available to me in the front in advance, so I have to do something. Okay, so what we will do is the following. So let me digress and talk about another data structure called trees. So trees is over a set S of ordered pairs. Okay, so let's say K1 P1, K2 P2. So it is a data structure that stores pairs of values like this. Okay, so there are all some numbers. Ki's, Pi's are numbers. And is a binary tree with each node having a Ki, Pi. Such that it is a binary search tree on K values, and it is a min heap or min priority queue, okay, on, so these are priority. So it's a binary search tree and a heap. Okay, let's look at an example. Okay, let's take a simple example. Okay, so this is a tree on these 4 pairs. If you look at the first coordinate, it is a binary search tree, right? 4 is less than 6, 5 is less than 6, so anything here is smaller than this, and 7 is bigger than 6. So anything on the right is bigger than this. Okay. Good question. We'll come to that. And if you look at the second coordinate, it satisfies the min heap property because the priority here is 1. These guys have 2 and 3, and this guy has 8. So it satisfies the min heap property. Okay. Is it possible to build such a structure? Yes. I'll ask you a question and your answer will tell you, is it possible to construct it? What should be the root? Minimum? Priority. Take the minimum priority, that should be the root. Right? Now, what should be the left one? Take the key, anything to the left of the key, they all should belong here. Build a tree upon them. Anything to the right, build a tree upon them. Okay? Okay. Let's think about how do I insert into a tree. Okay.
These order pairs has to be like 6, 1 and 5, 1.
Sorry.
Can this have two numbers repeated values?
Yeah, you can. I mean, you can, but yeah, because your binary search tree property allows you to have anything less than or equal to the key and anything the right is greater than or equal to. Similarly, the heap also tells you that the child should be greater than or equal to the parent. So it allows, but we can keep them simple and have them different. So suppose I want to insert 6.5, 1.5. Just want to be okay. So what do? Compare it with the root. So first look at the binary search tree part of it. Ignore the priorities for now. So 6.5 should be to the right and it should be to the left of it. So I'm going to add it here. Yeah, now what do you do?
Now you compare the.
Yes, there is a violation. So swap what? You,
This will go to the right.
so if you swap,
Swap, yeah.
you can't swap
You
like
this
what you.
the root, and if it was in the left, then this definitely has to go to
So there is a, what did we do? This is
rotate.
rotate. Exactly. So rotate right? So 6.5, 1.5 will come here and 7, 2. The rotation ensures binary search tree property. We saw that. That's what red black trees, AVL trees, they all use rotation. So I am doing a right rotate here. So 7, 2 comes here, 6.51 goes here, and this is seeing this. There is still a violation. No, now it's fine. So I can stop. If there is still a violation, then do a rotation. Basically, keep doing these rotations. Okay. So the time for insertion and deletion would be very similar. And the time for insertion or search all correspond to the height of the tree. Okay. Okay. So now let's back up to the. So I mean, why did I come here? I said, look, I have a sequence of keys which I want to insert and build my binary search tree, but I want to have the behavior of a random permutation. Okay. And build this binary search tree because then I can have the nice features like expected height is logarithmic kind of things. So what we will do, so the keys are coming in, I would get a random priority. Okay. So no, so I just pick a random number between 0 and 1 or something, it could be, so what am I saying? So I have this K1, K2, Kn keys coming in one by one, and I want to insert it into my binary search tree. But I don't want to insert it like this. I want a random permutation and then insert it. Okay, that will have the nice property. But I don't have all the keys in advance, so I can't do random permutation. So what I will do is, so K1 comes, I will construct a random number and I get a P1. Then insert it into the tree K1 comma P1. And the next one comes, so if you think about it, what is this binary search tree? What I have finally is that, so arrange your priorities in sorted order. Okay, so then I can have 6. So 6, 7, 4, 5. If these are the keys that came in this order. Okay, ignore this order, but 6 came first, 7 came 4, 5, and I build a binary search tree, I will get exactly the binary search tree I will get, which the tree, right? Because 6 will be inserted, and then comes 7, so 7 goes here, 4 will come here, and then 5 will come here. Right? Because if I had inserted 7 first, the tree I would get is slightly different. So 7, 6, 5, 4 is what I would get it if I insert it in the order in which I draw the keys, right? If I just don't do anything else. But if I insert it in increasing order of the priorities, then this is the key I would get. So this is exactly the key I would get by the tree. Okay. So for every key which I want to insert, I go and get a random priority and insert it into my tree of KIPI and do all these rotations, and so that the priority satisfy the min heap property. And finally, if you look at the tree, that tree is exactly the binary search tree I will get if I order the priorities in increasing order and insert it and don't do anything. Okay. Since I am consulting a random number generating to get these priorities, the sorted order of the priorities will be a random permutation of the KIs. So I have all these nice features here.
Do we know the fixed length? I mean, how many we are?
We don't need to know, because the priority is some random number between 0 and 1. Okay, so this is the use of trees. So this is like, it's like, right, in quicksort you are building in randomization by doing random permutation. In randomly built binary search tree, instead of assuming a random order, we order it, insert it in the way it's coming, but use a random priority to have the effect of random permutation, and then a binary search tree at the end of that type. So then the expected height, expected running time for insertion, all that will be log n again.
Is it like used in practice where you don't have all the insertions in a single, like the elements in one?
I mean, if I care about worst case, we can do all this, because this achieves worst case log n anyway. But yes, these are, yeah. Because all of this is geared towards the situation where elements are coming one by one anyway. So, okay.
So can you explain the last part again of like the
So what I am saying is, look at this tree. I mean, ignore the randomness, priorities, and all that. I defined you what a tree is, and I told you how to insert it into a tree. So now what I'm saying is, so here are the keys that are coming in. You know, maybe after this it is 6.5, 1.5, and I built a tree. Now suppose what I do is, I order these keys based on the priorities and insert them. There I don't do any rotation, nothing. I just insert them as they come. Only thing I do is, so order them, so it will be, 6, 1 would be the first, 6.5 would be next, because its priority is 1.5, 7, 4, 5. This is the order. If I insert into my binary search tree in this order and don't do any rotation, then this is exactly the tree I get. Okay. So another way to think of this key priority tree is basically order it based on the priorities in sorted order of the priorities, and just build a binary search tree without doing any rotations or anything. That will be the final tree. Now, I know that if I have keys coming in random order and I just build a binary search tree without doing anything, that binary search tree has some nice properties. The expected height is log n, but keys are coming in some arbitrary order. So I consult a random number generator, attach a priority, think of it as a ki pi coming into a tree, and build a tree. Okay. So which means that when I insert k10 p10, it might just, the rotations to ensure that this p10 min heap property is satisfied, the k10 may settle down somewhere else, not necessarily at a leaf. it may go down. So I build all this tree, final tree, and I'm claiming that that final tree has this nice behavior. Why? Because if you sort these priorities in increasing order, and if you had inserted keys in that order, the final tree you have now is the same tree. But that increasing order of the priorities is a random permutation because I'm just consulting random numbers here. So it is just a random permutation of the keys, and that's the way I've inserted it. So the final tree has expected height log n and expected insertion time small and things like that. Okay, so good. This also can be formally analyzed. What is the expected running time for insertion and all that? But I just wanted to tell you, about this data structure and this nice feature. Okay, fine. So the last thing which we will get to is Splay Trees. So this is like a random tree, right? Because you are given only keys and priorities, you obtain it randomly and take the ki pi and build a tree on it. Yeah. Yeah, so this is again some great idea by Slater and Tarjan, who pushed this whole idea of amortized complexity. And this is a lot of open directions and lots of papers written on them. Okay, so what do they say? So again, the idea is to obtain some sort of a balanced search tree so that you can support these operations: insert, search and delete in logarithmic time, also split and join. But now we worry only about logarithmic amortized time. So that means over a sequence of operations, the average time is order log n. So what they say is the following. Okay, so even for during search, okay, so let's say you are searching for some element, you follow your search path, and either you found out that it is not there or you found your element, then you already done this much work. So why don't you somehow adjust your tree and make it useful for future searches and other insertions and so on. So these are also called self-adjusting binary search trees. Okay, so one idea is, it's motivated by several things. I'll tell you later. That let's say I found my search element X. Yeah, so there is this philosophy of caching, where if you search for an element, it's very likely that you're going to search for it again and again, right? If you think about your mobile number or something, right? So you go and land in some place and you call some number, for the next 5 days, you are likely to call such numbers. So you might as well do something to bring it to closer to the root so that subsequent searches are cheap. So, but in the process, somehow you want overall time for a sequence of operations to be logarithmic. So one idea is, let's say I bring it to X. How do I bring it to the root? How do I do it? Maybe I do some rotations, single rotations. So it's actually
Do you want to bring it closer to
you want to bring it to the root. I'll tell you why. I mean, okay, so this is, let's say I search for 5, okay. I want to bring 5 to the root by doing rotations. So I'll do a left rotation at 4. So I have, it will be 5 followed by 4. Then I do a left rotation here to bring 5 up down here. So it will be, yeah, so if I do a left rotation, what happens? 5 goes here, 3 comes here, and 4 will be here. Okay, so then your 1 and 2 will be, the tree will be looking like this. Right, because one left rotation will make it like this. Then I am doing a left rotation. So 5 will be here, 3 and 4 are here, like, yeah. Then I am doing another rotation. So it will be 1, 5, 2, 3, 4. And one more rotation, 5 will go up, and the final tree will be like this. Okay. This is not really good because now you can call for a search to 4. So if if your tree is looking like this, because we are not going to do any balancing, because the whole point of doing splay trees is somehow it's self-adjusting. Okay, so no, I have to maintain a balanced binary search tree property. At the end, it has to be a binary search tree, right? So that this is how this is a binary search tree, because anything 5 goes up here, and this 1, 2, 3, 4 is on the left, and it follows that path. So now, if you give a call to 4, if this is the tree which takes linear time to access 5, then 4 is going to take a linear time to access it. It's really not going to help you on the amortized time. So this kind of, I'm just giving you an example where it does not work. No hope of expecting amortized logarithmic time, because you might have, you've not done much to the shape of the tree if you look at it. Okay. So their idea is not do single rotation, somehow do double rotation. Okay, that has certain magic. We'll see. Okay, so let's add maybe one more and see. So what we'll do, we'll look at the. So this is a node I'm searching, inserting whatever. I look at its parent and grandparent, and then look at a double rotation. So what happens is 6 goes here. So when I do a double rotation here, 6 should go to the root. Okay, so it will look like this, and then it's 3, 2, 1. Okay, at this point you don't see a big difference, but 6 has not moved to the root yet, so I'm going to do more. So let's do one more double rotation here. So 6, 3, 2, the double rotation will make it look like 6 goes to the parent, it will be 3, 2, and now let's stick in the other subtrees. The 5, 4 will be here, right? Because I'm doing a double rotation here. Let me write down the subtrees here, A, B, and this is my C, and there is D here. Okay. So when I do double rotation, this will become 6, 3, 2, and then this A will come here, B will come here, which are empty at this point, and this C comes here, and D will come here. Binary search tree property. All I am trying to ensure is that binary search tree property is satisfied. So the tree will look like this. 6 hasn't reached the root yet because there is still 1 there. So parent and grandparent. So, okay, how does double rotation, any rotation for that matter, so I have x here and y here, and if I do single rotation at right rotate at x, will make y here and x. But if you look at the subtrees, this is A, B, C. A will come here, B will come here, and C will come here. Right? Let's look at in the same way. Let's say this is x, y, and z, and I have some other things here. I mean, it's basically one right rotation followed by another right rotation. So let's do one at a time, maybe y and x. Then I'll have z, a, b, c, d. And then I do another right rotation, so that my aim is to make z go to the root, traverse to the root. So another right rotation will make me go away z, y, x, a here, b here, c here, d. So that's what I did. So now if you look at the final tree, okay, I have to bring 6 to the thing, so I'll do a left rotation. So I will have 6. One. There's nothing to the left of 1, so this will be empty. But what will go to the right of 1 is this portion. Because they're all, so there will be 3, 5, 2. So this will be my final tree. So somehow the longest path has become half of what it was. So this is the notion of path halving by doing this double rotations at a time. Right? Because there's some folding happening like this. How are we doing what? Oh, the last one, that's one, single rotation. Single rotation. Because I have only one, so this is just a single rotation, 6 goes up, 1 goes down. No, because if you think of, if you think of this picture, so this is my A, this whole thing is B, and this is C. So when I did the left rotation, A will be here, this B would be here, and the C would be here. So at this point, C is empty, A is empty, B is what it is. It will be like. Okay, so the actual implementation of a rotation is a constant time thing, which just changes the parent-child pointers of 2 or 3 nodes. That's all. Okay, so the key thing to note is that when we did this single rotation at a time, the final shape of the tree did not really change much, in particular the length of the longest path. But here it is becoming half of what it was. And so the hope and the fact is that if I do a bunch of these operations, the tree balances itself, that the total cost for this sequence, the average cost for a sequence will be log n. Okay, so let me just formally state their algorithm, what we will do, and maybe I'll try and prove one thing.
So what ends up being what happens with double rotation?
No, I'll tell you what. So so the algorithm now is, so you have this tree, binary search tree obtained from these operations. Now, after every operation, including search, insert, and delete, I'm going to do what is called a splay operation. Okay, and splay is essentially what I said is you've already spent so much time to get here. Why don't you do some rotations to fix things? That's intuitively what splay is. But more formally, what it will do is, let's say after a search, I searched and found my element, or I ended up at a leaf and did not find an element, right? At this point, I will look at this guy's parent and its grandparent. Depending on what the shape is, I will do a rotation. I'll explain you what the template is. Okay. So eventually, I want to move this to the parent, to the root. By doing this, 2 at a time kind of rotations, except for the last rotation, it could be a single rotation. Okay. So exactly what do I do? Well, and this is something I do after insertion, after deletion, everything. Insertion also, you go search and insert, and then start from that node and do this playing operation. Newly inserted node and start there. Delete. Again, if you remember how we did on the binary search, once you delete, you find its successor and go and replace that. So start from there and insert. There is a unique in order successor to that element. So you just go and find that, put that, and then start doing a splay from here. Okay. So how does a splay work, right? So you look at X is the node I'm splaying, and this is Y. Let's call it P, and look at grandparent. Okay. If it is of this shape, then I will rotate it to like this. Of course, the subtrees have a unique place to get in, which they will. Remember, the rotation ensures binary search tree property and all that, because just to sample, anything in C is smaller than GP and bigger than P. And that's true. Anything in C is bigger than P but smaller than GP. And it's bigger than X as well, because X is smaller than P. Okay. The rotation ensures binary search tree. So this is actually called, I think, zigzag rotation. Zigzag. Okay. If your X and parent and grandparent is looking like this, then the rotation being suggested is X is smaller than P. So I should put no. We will do this. Okay. Again, check that binary search tree property is satisfied, because if this is a tree, then X is bigger than GP because it's on the right subtree. Okay. So X is bigger than GP, and P is also bigger than X. P is bigger than GP, and all, and then the remaining subtrees go here. So this is called zigzag. And then there is a symmetric case. If it is right, then you rotate it to get a left. And similarly, if this could be, this shape, then you rotate it appropriately. Okay, so this is the template. And then finally, you may not have a grandparent. So then you will have X and your parent. You rotate it to X goes here and parent goes here. And the subtrees fit in where they should. No, even these guys, we saw this example. Here, all the rotations are like zigzag. Even then, when you see the final tree, it was like this. So one big path became like, two small paths. As you go up, they changed. So some sort of folding is happening. You need to really test it out and feel it. So now, what's the claim? The claim is so amortized cost of Okay, so of a splay operation is order log n. So what this is saying is that occasionally you may, so actual cost is actually the length of the path, because the rotations correspond to the length of the path anyway, right? The parent grandparent means the length is 2 and you're doing 2 rotations, otherwise you're doing 1 rotation. So the actual cost is the length of the path. So if you go and search for x and you found it here, the actual cost is that. But the claim is that the amortized cost, occasionally it may be n, the actual cost, but it just sort of balances itself that if you start from some tree and do some sequence of k such splay operations, it will be k log n over a long sequence. Okay, so we will actually try and prove this. So let me just state it in a way we will actually prove it. So
Until we get that extruded root,
yeah, all the way, right? I go search and then I keep doing, looking at the entire path, right? This is the path, found x, then look at its parent, grandparent and see which of the templates it belongs to, do the rotation. So x will move up just 2 steps. After 1 rotation, it will move 2 steps, because if you see everywhere x gets to the root. X was at the leaf, x gets to the root, x was at the leaf, x gets to the root, and similarly here x gets to the root. So then take that, its parent and grandparent, depending on the template, do a rotation, eventually x will go to the root. And that is what is the splay operation. The total cost is the length of the path, okay, the actual cost. But what I want to claim is the amortized cost is order log n. So what we will show is the following. Yeah, so let me define some. So for every node x, S of x is the number of nodes in the subtree rooted at x, including x. And R of x is log of S of x. Okay. Remember the way we saw amortized analysis for binary increment or multi-pop and various things. We had some charging argument, and I also mentioned some potential argument, right? You can define a potential function which tells you the amount of charge in the data structure, and then the amortized cost will be actual cost plus the potential difference, right? And I have been threatening you that the potential sometimes may not have any real meaning, and here is an example where people are still trying to understand this potential. So the potential of my data structure is summation Rx, this tree, binary search tree. That's sum of the logs of the sizes. So you have your tree. For every node, there is a rank. This is called a rank, which is log of the number of nodes here. Add all the ranks, and that is the potential in the tree. Okay. So for example, if your tree is so unbalanced, yeah, so what would be the potential? Because that will get us understand something. The tree is like a path. Okay. Then the number of, so this will be log n, right? Because number of nodes in the subtree is n. Log of that is rank. Here it will be log n minus 1. Here it will be log n minus 2, and so on. So when you sum them all, it's log n factorial. So this potential here is about n log n. Okay, but if the tree is nicely balanced, then this here it will be log n. Here it will be log n minus 1 twice, and this will be log n minus 2 for, because it's log n by 2, it's log n by 4, and you add them all, this will be more like order n actually. So this is, you expect when the tree is unbalanced, it should have a lot of potential because the operations need more time. So they will draw extra money from the potential. When the tree is balanced, the operations are cheap. It's going to take log n. So that's one way of connecting this potential with this. But all we are going to do to prove this is the following. So what the subclaim which we will prove is the amortized cost of a single rotation at x right. So it's like it was x was here, y, and then I moved it to x here and y. What is the amortized cost? I'm going to prove this to be 1 plus 3 times okay. So I have my, so now I'm not going to really analyze this entire Splay operation. Okay, what I'm going to do is this Splay operation, let me break it up into the amortized cost for each of these rotations. Okay, if I'm doing a single rotation, the actual cost is 1, and then I look at the difference in the potential. Right, that's what I'm supposed to do. And for double rotation, the actual cost is 2, and then I will look at the difference in the potential. Okay, and I'm going to argue the following. So if you do a single rotation, what is r prime? So r of x, so the tree changes, this is tree, the tree changes to t prime after you do whatever operation. So the ranks at the node x, here I'm going to call it r prime. Okay, so that's this r definition. Because the tree changes, x changes, x's subtree changes, so r of x will changes. The new r is r prime. Okay, so the claim is after a single rotation, the amortized cost is 1 plus 3 times r prime x minus rx, and this is one amortized cost for a double rotation at x is at most 3 times r prime x minus rx. And I claim that this is enough to show. Let's see what it is, right? So let's say I'm doing my Splay at this node x. Okay, so I do a double rotation, and I get a new tree. And remember, x goes to the root, and some other, maybe it's like this. Okay. Now, what is the amortized cost to go from here to the actual cost plus the potential difference, just for this operation, which I am going to prove is at most 3 times whatever the rank of x is minus whatever the rank of x here is. Okay. Then let me do another double rotation. X moves here, and what is the amortized cost? It's again actual cost is 2 plus the potential difference, which I am going to prove is at most 3 times r prime of x minus 3 times r of x. Okay. Now remember that, see, there is a telescopic sum happening here, right? If I finally, all I care about, let's say I don't even do single rotation, maybe the length of the path is even, okay? Then all I care about is the amortized cost between these two, right? The actual cost is 2 times or whatever the length of the path, which is all accounted for in the 2 plus 2 plus 2 plus everywhere, and the potential difference is 3 times r prime of x. That's what I care about. What I know is 3 times r prime of x minus r of x plus this r becomes r prime now minus this. So they all cancel out. And finally, it's 3 times rank of this minus rank of this. Okay. What is the rank of this? X. The final tree, what is the rank of x? Yes. Log of s of x, and x has become the root. So everybody, so it's at most 3 log n. That's it. That's all. So if I show this, I'm done. Okay. If I do single rotation, there will be a plus 1. That's all. See, the good thing is there is no plus 1 here, because I can't afford a plus 1 here, because so many double rotations I'm doing, that's corresponding to the actual cost, which could be as bad as n. But that's all absorbed here. So what we will actually show is the actual cost, which is 2 plus the potential difference, which I will show it to be less than or equal to this for each double rotation. For single rotation, 1 plus the potential difference, I'm going to show it to be this. But single rotation happens only once, so I can afford that plus 1. So overall, the amortized cost would be the actual cost, which is length of the path, where it's all accounted for in the amortized cost here, plus 3 times the rank of this node minus the rank of this. I even ignore this, and this rank is at most n, so that gives you 3 times log n. Okay. So now let's try and show this. This is not very hard, because when I move from here to here, potential is sum of the ranks. Not too many ranks change, right? Rank is log of the size, and size of subtrees, because not too many subtrees change. They all remain the same, so they cancel out. Only a few things change. We will account for it there carefully. Okay. So let's try and look at this double rotation. Let's do a single rotation first. So is that clear? Now I'm going to erase this portion.
How is the actual cost getting accounted for, which will be 2 into 8 of the
Actual cost is accounted here. This is the actual cost. When I am doing, actual cost is broken up into these rotations I'm doing. So when I'm doing a double rotation, 2 is accounted here. So 2 plus the change in potential, including this 2 is absorbed, and I'm going to say it's at most 3 times. And then there is another cost of 1 for this single rotation, but that one, let me add it, no problem. Okay. So basically the actual cost plus the potential difference is the sum of the actual cost plus potential difference of all these little pieces, and that's all absorbed here. So and this r prime x minus rx is a telescopic sum, because x keep moving up. So let's do it for single rotation. It's pretty easy actually. So I have, let's say it's x and y, and I'm doing a right rotation. X comes here and y comes here. So let's see, actual cost is 1, and what is phi of t prime minus phi of t, right? Well, it's phi of t prime is, take every node here, look at the log of S of x for every node, add them all, that's phi of t prime, same as here. But if you look at A, its subtree size has not changed. B subtree size, C subtree size has not changed at all. So they all cancel out. So this would be equal to 1 plus, very simply, r prime x plus r prime y minus rx minus ry. Because only x and y, their ranks change. Right? Okay. And I have very comfortable this thing. So let's see if there is a easy way of saying this. So I want to show yeah. What do we know? R prime y is less than or equal to r prime x. Right? Because the rank of this node, r prime is all happening here. Rank of this node is less than or equal to rank of this because it's all log of s of x, clearly. So this r prime y I can replace, so I can write this as less than or equal to 1 plus 2 r prime x. And if you look at the r, it's the other way. R of y is greater than or equal to r of x. So it's clearly, that's it. So what did I do? R prime y I replaced by r prime x. So that became 2 r prime x. R of y I replaced by r of x again, but again they are working in the right direction for me, so I have this. So that's this. I don't even need 3, but 3 I really need it for here. Yep. Okay. So let's try and show for this, then I'm done. There is a symmetric case for zigzag, this kind of trees and so on, but the argument is somewhat similar. So this is clear for one rotation. Because the key thing is to absorb that I don't want to have a 2 here because that will add to my path. This is captured by the potential drop somehow. Okay, so let's look at this. So again, actual cost is 2 because I'm doing 2 rotations, and potential difference is r prime x plus r prime p plus r prime g minus r of x Okay, so then this I need to look at my notes. There is something about log being concave and all that. So let's observe the following. R prime x is equal to r of g. So this is just g for grandparent. Okay, do you agree with all of this? R prime x and r of g are the same because everybody below a, b, c, d, x, p is below them. R of p is greater than or equal to r of x, and r prime p is less than or equal to r prime x. So I can write this as less than or equal to 2 plus somehow 2 I want to the amortized cost. Actual cost 2 plus the potential difference. So I think I will cancel out r prime x and r of g, and r prime p I'm going to replace by r prime x. Maybe I'm going to keep r prime g as they are, and r of p is greater than or equal to r of x, so I'm going to write this as minus 2r of x. Yes, r prime x plus r prime g minus 2r of x. Exactly. Okay, good. So, now we need you need some log being concave somehow. Um, okay. Okay, so what we know, log of a plus log of b by 2 is less than or equal to log of a plus b by 2. Right? Some geometric mean, arithmetic mean business. Because log of a plus b, log of b by 2 is log of square root of ab, which is geometric mean. And a plus b by 2 is arithmetic mean. So logs are same. So now I'm going to plug in, change some symbols. So I need to rx plus r prime z. So rx plus r prime g. So that's this. S of x plus is this thing? Yeah. So S of x plus S prime of g. Yeah. So see, S of x is this, the size of x, this subtree, and S prime of g is this. And they are disjoint, as you can see. So it covers a, b, x, c, g, d. The only thing that does not cover is this p. So all I'm saying is that this sum, S of x plus S prime of g, is at most S prime of x, because S prime x has even more, for example, p. So now we are done, because what I have is r prime x, r prime g, and so on. So let's see, what do I get? So this is equal to r prime x minus 1, because log of S prime is r prime. Right. So I want to get rid of r prime g and then I'm done. So what do I get? R prime g is at most 2 r prime x minus 2 minus rx. So let's take this r prime g and replace r prime g by that. So what do I get? 2 plus, see the good, okay, r prime x plus r prime g is at most 2 r prime x minus 2 minus Rx minus 2Rx. The great thing is the minus 2 for me, which kills this, and I have 3R prime x minus 3Rx. That's what I want to show. Okay, so somehow this log nice property, and you look at this subtrees and argue something about it. Yeah, and there are other cases, if the tree is like this and I change it to something like this, play around with this kind of some equations, calculations, and you can argue all the time it's this. So the cost of actual cost is paid by the potential drop here, really, and in this case. Here we pay for it, but that's just only once and one. Okay. So that overall shows that if I am splaying at a node x, the amortized cost is order log n. Because basically, it's r prime x at the end minus r of x, but r prime x is log n 3 times. Okay, so they had this in 90s, and then people were looking at why this, and there are slight variations of the potentials for which this still works. Why this potential, why this kind of rotations, can you do various other kinds of rotations, splaying, variations of splaying, that's all have been looked at. Some answers are known. Yeah, and the fact that this brings, so this is a lot of other nice features as well, apart from the fact it's self-adjusting, right? So the cool thing, it's compared to balanced binary search trees, you don't need to save color or the height or any such values. It's just, you just need the keys and the pointers, and you just do this playing. Now, so suppose I have some keys, and I tell you that this, so I have the keys and I have to build a balance search tree, but I tell you that K1 is searched some P1 times, K2 is searched P2 times, and Kn is searched Pn times. Now, can you construct a binary search tree? Nothing about balanced or anything, because it need not be balanced, because if something is accessed very infrequently, you don't mind spending linear time for it, and something is accessed very often, you may want to keep it close to the root. So can you construct a binary search tree such that the weighted cost of the search is minimum, right? So that means K1 times P1 is a frequency, let's say F1, I don't want to call it P1. P1 sounds like probability, but you can. So K1 is searched F1 times, K2 is searched F2 times, Kn is searched Fn times, and I want the cost of searching Ki times Fi, the summation, to be minimum. What kind of a search tree can you come up with which will minimize this? Okay. Now it turns out if you give me the keys and if you give me the frequencies, one can actually construct this optimum binary search tree using dynamic programming. Okay. We will actually look at it when we do dynamic programming. Now, the beauty of Splay Trees is it automatically constructs this optimum binary search tree, because of this thing that the key that's accessed more often is brought close to the root, which saves the cost of accessing the key later, has this automatic behavior. So not only Splay Trees have amortized logarithmic cost, they also give you the optimum. I mean, they are constant times a factor of compared to the optimum. Look at the cost of this search tree, and look at the cost of Splay Trees, where you access K1 F1 times, K2 F2 times, but you don't know F1 F2 F3. It just sort of does this playing thing. The total cost will be constant times the cost of this optimum binary search tree. Okay, so there are some very nice features about Splay Trees and some interesting, some open problems as well, which are not it resolved. Okay, I think I will. Good summary of some of the recent stuff on balanced binary search trees. Yeah, okay.